Hi everyone, welcome to our video series on feature engineering. We are discussing feature selection category and focusing on embedded techniques. The key point with embedded methods is these methods are seamlessly integrated into the machine learning model. That's something very new. So let's get started. Let me just show you what we have already discussed so far in terms of feature engineering techniques. So we have covered filter method and wrapper method. Just a second, let me get the highlighter here. Yeah, so filter method, wrapper method, and under filter method, we have covered the variance threshold, correlation threshold, and discussed a couple of, or in fact, three types of correlation: information value, univariate feature selection, and hypothesis testing. Select k-best, wrapper method, and now we are discussing embedded method. And under embedded method, we are going to talk about lasso, ridge, and elastic net. So the topic is divided into two parts. One is regularization. The first part we will cover is the intuition behind regularization. Why do we need it? And we'll take some simple example to understand regularization concept. And then in the second part, we will deep dive into technical explanation step by step of L1 and L2 regularization. Some of the prerequisite, little bit of Python and fair amount of machine learning experience, especially regression concept and machine learning concepts like overfitting and so on and so forth. And a little bit about maths, gradient and derivatives would be really handy. So what is the meaning of embedded method? Embedded methods are nothing but a process of selecting useful column during the training process of the machine learning model. That's pretty unique um, about embedded method. So why do we need it? We want to streamline and optimize the model building process, which should take care of which columns and which features are useful. And secondly, by selecting the relevant features during the model building or training, we can reduce the overfitting and we can get the model more generalized. This is also very useful when we deal with high dimensional data sets. So some of the benefits here is going to give you computational efficiency. It prevents overfitting. We'll see how it is done. And overall is going to give us a better generalized model. Most importantly, because of the L1 and L2 regularization, we are in a position to explain why the model picked up a few features and why it dropped a few features. Regularization also handles multicollinearity. We talked about it in the previous video, how multicollinearity can lead to sometimes, a serious situation with overfitting. So the techniques of embedding, firstly, there are machine learning models based, for example, here, decision trees and random forests, and then boosting algorithms, support vector machines, and logistic regression. All of these models have capabilities to provide L1 and L2 regularization. But we're going to discuss the regularization, which is a basic regularization technique, lasso, ridge, and elastic net. So what is regularization? First, look at this simple example. Let's say you decide to memorize every page or every detail of your textbook, including all trivial details. Now, after having done that, you can recall anything and everything from the book during the practice. But when you are faced with new question that is slightly different than what you saw in the book, you will not be able to answer it properly. because you have memorized the book too well. And this situation is called overfitting in machine learning. Now, with the regularization, which is kind of a balancing act, let's look at the example again, the same example. Now you are advised to understand the main concepts of the book, really not focusing too much on every detail like page number and paragraph number and sentences and which page this particular text is and so on and so forth. Rather, you're focusing on the main concept. So this way you can grasp the topic and subtopic very well, and when you are faced with a question, you will be able to answer it properly. Now this is called regularization in machine learning. Is similar to what we just discussed, essentially finding a balance between all the details in the data and coming to a level where you're talking about abstract of the data or key concepts in the data. So L1 and L2 regularization, these are two flavors of regularization. So what is L1 regularization? It's like telling your friend if a specific point or a topic or maybe keyword is not crucial, then simply forget it. This is called L1 regularization, and we will see how it is done in terms of machine learning. On the other hand, L2 regularization is like saying, okay, you consider all the points, but don't get too fixated on every detail, but rather maintain some kind of a balance. That means you're not forgetting it, not completely ignoring every detail. In fact, you're considering all the details, but from a distance. That's called L2 regularization. Let's take an example, how it will look like when we train a model using L1 regularization and L2. I'm taking an example of, linear regression. If you look at it here, this equation is very, very, simple and popular. So after applying L1 regularization, notice what happens. These are your coefficients. So these are your coefficients of the column, like, W1, W2, and Wn. That's what is ABC. I've just mentioned ABC. So after L1 regularization, before regularization, it was 0.2. After regularization, it could become 0, depending on how important that coefficient is in the model. Similarly, D, which was before the regularization, some value, but after it is 0. And likewise, E is another example where the L1 regularization turned E into 0. So this is called L1 regularization. It is similar to what we just discussed in the previous one, that simply forget it. Like here, don't consider all the details. If you feel that detail can be uh, very inconsequential, then simply forget it or ignore. And that's what you see here in the data set. And that's what is going to happen in the Python code when I show you. Let's look at L2 regularization. Now, same thing. You have all these coefficients on the left-hand side here, before regularization and after regularization. Notice the values are getting optimized or shrunk. And this shrinking of coefficient is called regularization. But in this case, none of them become 0, which was the case in L1. L2, none of these coefficients will be 0, but most of them will be close to 0 or a smaller value. But the question is, why do we end up with high coefficients in the first place? When we train our model on a data set, why do we end up with high coefficients? Some of the reasons are, of course, the high magnitude of the coefficients can be an indicator of overfitting. This could be the reason for high coefficient could be because of overemphasis on the training data. like memorizing every noise and every column and every point in the training set. Multicollinearity can also be the reason for high coefficients. Overly complex features like polynomial features, nonlinear data, too many features can also be the reason for high coefficients. Capturing all the noise in the data underlying patterns can also lead to high coefficients. Let's look at simple intuition on regularization. I'm taking a simple example. Let's say, this is how our data set is represented using quadratic polynomial. This is just a simple, trivial, representative example. And the blue dots that you see here on the plot, these are your training samples. And the red one, this line that you see here, this is your regression model. And notice I have trained with the degree of 15. Now, most likely it will actually overfit, and that you see it very clearly. The model is actually touching all the training points, all the noises, and all the unnecessary information also. The model is fairly, close to most of the training points. That is called overfitting model. But when we regularize, it's not going to be touching all the training points. But notice here, the brown line is your regularized model. Notice how smooth it is. And that's the intuition behind regularization. Now, one difference or one key thing that you notice here is with the red line, the training error will be very less, maybe like 0, but testing error will be very high. That's the sign of overfitting model. Regularized model, this will not be 0. This will have some non-zero value. That means that the training error, there will be some training error, whereas the testing error will slightly go down. That's the objective of regularization. So essentially, what we are saying is regularization enables the model to learn important features in the data without really worrying about all the noises and outliers and all the data points. So why should we only learn important features? This should be very obvious. Let's look at this simple data again. And I'm training the three models with the polynomial of degree 2, degree 10, and degree 20. Notice here you have a smooth model going through the point. Here is somewhat overfitting. This is definitely way too much of overfitting because it is going through each of the point. So what will happen with this situation is, let's say the black dots are your training points, and with the normalized model or regularized model, the mean squared error could be like this, 0.01. With the overfitted model, notice the mean squared error is more, and even more with severely overfitted model. That's the reason um, we should only learn the important features. So in this particular model, you see the model is only learning important features. Now, features simply means the value in the two-dimensional space. So this is the value that the model is actually learning. It is not really touching all the points like you have here and here. All right. So this is the meaning of, this is the reason why we should uh, learn only the important values or important features. So what is overfitting? Is a model which learns the training data very well, and it captures all the noises and fluctuations and specific pattern in the training data. And that's the reason the model does not generalize well when it comes to predicting a new sample. The key characteristics of overfitting that it will memorize all of the training data, result in poor generalization, and the model is too complex. And this also results in high variance model. That means the predictions are highly sensitive to changes in the test data. So high variance model in machine learning refers to the sensitivity of the model due to small fluctuations. And most cases, highly varying model leads to also overfitting. So let's look at another example here of polynomial degree 20. And I'm running a lot of test sets like set 1, set 2, set 3, and set 15 here. High variance and low bias model because of the high degree of polynomial. And you notice here how the values here are changing with a little change in the set 1, set 2, set 3. You notice how the mean square error is fluctuating. Whereas the low variance model, among the set 1, set 2, set 3, because I have trained trained the model with degree of polynomial 2, the mean square error is fairly consistent, or you can say constant. I hope this example clarified what is overfitting and what is high variance and low variance model. Now, in the second video, I'll be walking you through the technical explanation of L1 and L2. See you in the next session.